In this recording, we want to look at the concept of continuity. We say that a function is continuous at an interior point C if the limit as x approaches C of f of x is equal to f of c. What that means is the limit as x approaches C has to be the same as the function value at C. In order to be continuous at an endpoint, at a left or at a right endpoint, to be continuous at a left endpoint, the limit as x approaches A from the right has to be the same as f of A. To be continuous at a right endpoint, the limit as x approaches B from the left has to be equal to f of B. Now here's an example. We want to talk about continuity at points. Now let's start with x equals 0. The limit as x approaches 0 from the left is 1 and f of 0 is 1. So at 0, this function is continuous at the left endpoint. However, let's look at 1. The limit as x approaches 1 from the left is 0 and from the right is 1. Now since the left and right hand limits are the same, this limit does not exist, so it is not continuous at 1. Now let's look at 2. The limit as x approaches 2 from the left and from the right are both 1. However, f of 2 is 2 and not 1, so it's also discontinuous at 2. If we look at 3, the limit as x approaches 3 from the left and from the right are both 2. Also, f of 3 is 2, so it is continuous at the point 3. Now let's look at the other endpoint, which is 4. The limit as x approaches 4 from the left is 1. However, f of 4 is not 1, so it's not continuous at the right endpoint. When we think about continuous graphs, we can think about a continuous graph as a graph that we can draw without picking up our pencil. So as we draw this graph, when we get to 1, we have to pick up our pencil and move. And when we get to 2, we have to stop and pick up our pencil and draw the function value. So it's discontinuous at 2. Between 2 and 4, we never have to pick up our pencil, but when we get to 4, we have to pick up our pencil to make our function value. So it's discontinuous at 1, at 2, and at 4. Now here's an example of a function that's continuous at every point in its domain. Now notice we have the square root of 4 minus x squared. Its domain is only between -2 and +2. And notice I can draw this picture without ever picking up my pencil. It's continuous at the leftmost endpoint because the limit as x approaches -2 is 0 and f of -2 is 0. It's continuous at the rightmost endpoint because the limit as x approaches 2 from the left is 2 and f of is 0 and f of 2 is also 0. Here's an example of a function that is right continuous but not left continuous at the origin. As I approach 0 from the left, all of my y values are 0. However, f of 0 is not 0, so it is not continuous from the left. It is continuous from the right because the limit as x approaches 0 from the left is 1 and f of 0 is 1, since that's where the shaded dot is. So this has what's called a jump discontinuity. It's discontinuous at 0 because it jumps from one place to another. Now the continuity test has 3 parts. In order for a function to be continuous at the interior point C, f of c must exist. The limit as x approaches c of f of x must exist. And not only must those two exist, they must be equal to each other. So the limit as x approaches c of f of x must be equal to f of c. Now here are some examples of functions. The first function is continuous at 0. As we approach from the left and from the right of 0, our graph approaches 1. f of 0 is also 1, so it passes that continuity test. This graph is continuous at 0. However, if we look over to B, the left and right hand limits as we approach 0 are both 1. However, f of 0 does not exist because there's a hole here. And so since f of 0 doesn't exist, it's discontinuous at 0. If we look at this graph, f of 0 exists here, but it's not equal to the limit as x approaches 0, which is 1. So the limit as x approaches 0 is 1, but f of 0 is 2. So this is also not continuous at 0. This is the example we looked at just a second ago. The limit does not exist, and therefore it is not continuous at 0. If we look at this example, f of 0 does not exist. If we plug 0 into this function, we'll have 1 divided by 0 squared, which we know is undefined. So since f of 0 doesn't exist, it's not continuous at 0. And this one is not continuous at 0. This has what we call an oscillating discontinuity. As x gets closer and closer to 0, then 1 over x is going to get larger and larger and larger. Now remember, sign of any number is always going to be between -1 and 1. So this just oscillates between -1 and 1, -1 and 1, -1 and 1. And so it does not have a limit as it approaches 0. So it's discontinuous at 0. Now a continuous function is one that is continuous at every point of its domain. A continuous function may not be continuous on every interval. Here's an example. This is not continuous. This graph y equals 1 over x is not continuous on every interval. It is continuous from -infinity to 0, not including 0, and from 0 to infinity, not including 0. However, it's undefined at 0, and so it does have a point of discontinuity at x equals 0. But a continuous function is just one that's continuous at every point in its domain, and this is continuous at every point that's in its domain because its domain is every number except 0.